These are the solutions to the work and energy review for our energy unit. So let's start with number 1. We've got students who want to calculate the work done by friction. So we're calculating a kind of work. We need to remember every time we see work, work is a force times a distance. So if it's the work done by friction, it's the force of friction times a distance. For an object moving along the surface, they can measure force, they have a meter stick and a stopwatch. Which of the following will allow them to take the measurements needed to calculate the work done by friction. So remember, work is force times distance, so they need to know how much the friction is and they need to know how far it goes. So they don't need time, so we can eliminate anything with time on it, so that helps. We don't have A or B, they're going to pull it. Now, if the acceleration is 0, the force by the probe and the force of friction on the object are equal to each other, just like you guys did in your lab. So if that's the case, pulling the block at an unknown constant speed with 0 acceleration with the force probe for measured distance is going to allow you to calculate the work. All right, the next one, a cart of unknown mass moves with a known speed in the figure above. It hits a sensor and rebounds. So the sensor measures the force as a function of time and a function of position, and we need to know what can be used to determine the cart's speed after it rebounds. So speed after it rebounds is going to be the final velocity, and it's telling us here that it has a known initial speed, initial velocity. So when we look at this, we have a force versus time graph and a force versus position graph. For a force versus time graph, the area is force times time. That's impulse, and that's change in momentum, which is mv final minus mv initial. For the force versus position graph, the area is going to be the x times the y, force times position. That's the same thing as work. We know that work is equal to the change in kinetic energy, and that's 1/2 mv final squared minus 1/2 mv initial squared. So what we see with these two is that because we know the mass and we know the initial velocity in each case, the only unknown that we have for each one of these is the final velocity. We can use the graph to get the area. And so what we see with this is that either graph 1 or graph 2 can be used in this situation because they're both going to give us information to allow us to find the final velocity with what we already have. All right, question 3, we have this athlete running. So the first athlete, 50 kilograms, runs 10-meter high platform with the rope, swings to a height of 1.8 meters above the ground. Later, a heavier athlete running at the same speed does the same thing. We want to know the maximum height to which the 100-kilogram athlete swings. One thing that we need to keep in mind as we're looking at this is that yes, the 100-kilogram athlete, because kinetic energy is 1/2 mv squared, is going to have twice the energy. But when we look at it, when we look at this for the 50-kilogram athlete to begin with, we know that his initial kinetic energy is going to be equal to the final potential energy. So that's 1/2 mv squared, and that's going to equal mgh. And as we do this, it's the same mass on both sides, so they cancel out, which means that the speed and the height depend on each other, and it doesn't have anything to do with the mass. So if he's going a speed of v and goes to a height of 1.8 meters, anything of any mass running at that speed of v is going to go to the same height. So the next athlete, who happens to be 100 kilograms, is going the same speed. Even though the rope is different, even though they have more mass, they will rise to the same height. For the next one, we have this pendulum, and it's a maximum height h above equilibrium. And we want to know what's true about the total energy of the Earth pendulum system. If we're talking about the Earth pendulum system, that means my energy is going to consist both of potential energy and kinetic energy, remembering that because Earth is in the system, we are going to have potential energy. That means those two are going to exchange it between each other. Potential energy gets to be part of the total energy of the system, And so that means that the total energy is constant throughout the pendulum's motion. If the Earth were not part of a system, then we would see the kinetic energy of the pendulum increase and decrease, and since there's no potential energy, it would change. But here, because the Earth is in the system, mechanical energy is going to be conserved. It's going to stay constant throughout. It's going to stay constant throughout. All right, next one, we have a rubber ball that's going to be dropped. Sorry about that. We have a rubber ball that's going to be dropped vertically from a height of 1.5 meters above the floor. It bounces, and it comes and loses 0.6 joules of energy, and then I want to know the maximum height of the ball after the bounce. And so what we're going to do is look at sort of three different spots. We start off here with potential energy, and then down here on the way back up we have kinetic energy plus that work lost in the bounce, what we'll call is energy dissipated, so delta E. And then we come back up to a lesser height because it's just this kinetic energy that turns into potential energy. So all throughout, energy will be conserved, it just won't be mechanical the entire time. So we know that energy at position 1 is equal to energy at position 2 is equal to energy at position 3, and then these are those positions. Energy 1 is our beginning height, energy 2 is coming right up off the ground after we've lost some energy, and energy 3 is that potential energy. And to keep everything the same, we're going to say that there is still that same change in energy at the top. Once it's lost, it's going to stay as that change in energy. So at the top, we've got mgh. They tell us that height is 1.5 meters. And then over here at the end, we have mgh2, which is what we're finding, plus that change in energy. So we're going to plug everything in. We're going to solve for h2. So we have 0.2 kilograms times 10 meters per second squared times 1.5 meters is equal to 0.2 times 10, that's m times g, times h2, which we don't know, plus our loss of energy, which is 0.6 joules. And the reason we're adding it is because that's in a different spot. Right? That energy can no longer be potential energy. So the more this grows, the more this is going to shrink. So once we have all those numbers in there, we're going to go ahead and solve for what we got. So we have 3 is equal to 2 h2 plus 0.6. Subtract 0.6 from both sides, so 2.4 is equal to 2 h2, and that second height comes out to be 1.2 meters. That's our second height there. Number 6, we got a spring scale exerting a force on a block, pulling it over a smooth surface. They repeat it several times, each time pulling the block from rest through a distance of 1 meters, which the following graphs of force as a function of distance will be moving the fastest at the end. So, for force as a function of distance, especially because we're talking about a graph, one thing that we need to keep in mind that's important for this is that the area of the graph is equal to work. Work is equal to the change in kinetic energy. And so since it starts at rest, it's just going to be 1/2 mv final squared. So, that means if I want the fastest speed at the end, I need the most area at the end. So we want to find the graph with the most area. Zoom out so we can see all of those. So if we look at it, this area and this area are the same. Area D is bigger than both of those. Area B is even bigger than that. So since this has the most area, it's going to have the most kinetic energy at the end, which means it's going to be moving the fastest. All right, 7 on this one. All right, so we have a graph that shows the force exerted by a spring as a function of time. A block on a frictionless table is pushed against the spring that's fastened to the wall. It's compressed until its length is 0.2 centimeters. The block is released. We want to know which of the following values is closest to the kinetic energy of the block when it leaves the spring. So, what's happening is that the spring is going to be stretched out. So when we look at it here, the spring has no force at this point. So the 0.3 meters is when the spring is not compressed at all. And we're going to push the spring back until it's compressed to 0.2. And so this is where we're at. So when we compress the spring, here's where we have energy stored in the spring. And then when we release it, that's all going to become kinetic energy for the block. So what we need to do is to be able to find the potential energy of the spring. We know the formula is 1/2 kx squared. The problem is we don't have a k, even though we have an x. But we do know that with a force times a distance, spring length graph, that the area of this graph is the work done on the spring, which ends up being the potential energy of the spring. And so when we look at the area in question, it's going to be this triangle right there. So it's going to be 1/2 times the force of 60 newtons times that distance of 0.1 meters, and that's going to be equal to the kinetic energy that the block has when it's released. So 1/2 times 60 times 0.1 is 3 joules, and that's equal to that kinetic energy right there. All right, part 2 of our review is even more problems about work and energy. So we're going to start off with the power needed to lift a 49 kilogram person a vertical distance of 5 meters in 20 seconds. So since it's asking about power, power is work over time. So it's going to be force times distance over time. When we're lifting something, the force required to lift it is that object's weight. So it's mg times the distance that we're lifting it over time. So it's 49 times 10 times the 5 meter distance that we're lifting it divided by 20 seconds. And when we do that, we get 122.5 watts, which if you use 9.8 ends up being 120 watts. Number 2, a warehouse worker uses a forklift to lift pickles onto a platform that is 2.75 meters above the floor. We have the mass of everything, and we want to know the power. We're going to find out how long it takes to lift the crate. So we know that power is equal to work over time, and in a situation very similar to what we have before, it's mass times gravity, so the weight of the whole thing, times the height that we're lifting it divided by the time. In this case, we are looking for the time. So when we rearrange all of that stuff, the time is mgh divided by the power. So it's going to be the entire mass, 207 kilograms times 10 meters per second squared times the 2.75 meters above the floor divided by 1440 watts, and that time comes out to be 3.95 seconds. And again, if you used 9.8, you would end up getting 3.87. That's just where I pulled these problems from. Number 3, if you double the speed of an object, its kinetic energy is, well, kinetic energy is 1/2 mv squared. Since the speed is squared, doubling it is going to have bigger consequences. So if we look at a situation where we have 1/2 m times 2v and we square it, both things have to be squared. That ends up giving me 1/2 mv squared times 4. That's 4 times the kinetic energy. So doubling the speed gives me 4 times the kinetic energy. Tripling the speed would give me 9 times the kinetic energy. We know that increasing velocity increases energy. In this case, we have to square the particular increase that we're doing. Question 4, we have this mass sliding along the ground. It's going to hit a spring. We have the spring constant. We know how far it compresses it. We need to know the initial speed of the block. So it's moving this way with the initial velocity, which means we have kinetic energy at this point. And then once we compress the spring, all of that kinetic energy is spring potential energy, telling me that 1/2 the spring potential, so kx squared is equal to 1/2 mv squared. We're going to take this and we're going to solve for the velocity. So that speed ends up being the square root of k over m times the compression squared. So it's the square root of 500 divided by 2.5 times the compression of the spring, and I think I did the conversion wrong, so I'm sorry about that. That should be 0.05 meters squared. And when you do all that, the speed at the beginning ends up being 0.71 meters per second. 0.71 meters per second. The next one, we start off at the top and go to the bottom. At the top, we have potential energy, and we have friction opposing the block, so it comes to a stop 2.5 meters from B. I want the coefficient of kinetic friction between the block and the surface after position B. So what we're going to say is that here at this point, if we look at it, we have just potential energy. When we get down to the bottom, from A to B, it's frictionless, and so when we get down to B, all of that energy has become kinetic energy without any loss, and then we come to stop some point a little bit later, and so we don't have any kinetic, we don't have any potential. What we have is energy lost or work done by friction. That's where all of our energy is. And so we know that the potential energy at the beginning is going to become work done by friction at the end. The potential energy at the beginning is mgh. Work done by friction is the force of friction times the distance that we move, because that's the work done by any particular force. We'll zoom in on that right now. So we've got mgh is equal to the force of friction, which is mu times the normal force, but in this case the normal force is going to be the weight of the object times the distance that we move. Well, what we see here conveniently is that there's an mg on both sides, so it crosses out, and if I want the coefficient of friction between the block and the surface, mu is going to be the height over the distance, so mu is going to be where's my height? 1 meter, sorry, 1 meter divided by the distance that we slide at the bottom of 2.5 meters, so 1 divided by 2.5 ends up being 0.4. That's my coefficient of friction. This is a difficult problem where we had to put a lot of things together in order to find it, but the big idea here is that the potential energy is turning into work done by friction. You just may need to know how to find that work done by friction. Let's move on to number 6. Number 6, same situation. We want to know the speed of the block at point B. So in this case, we're going from potential energy at the beginning to kinetic energy at the bottom of the hill at point B. And it is frictionless, so there's no loss. All of that potential energy, mgh, is going to become kinetic energy, 1/2 mv squared. The m's cross out, and that speed ends up being the square root of 2gh. So 2 times 10 times that height of 1 meter, we get the square root of 20, which is roughly 4.4 meters per second. Number 7, the weight of an object on the moon is 1/6 its weight on the Earth. A body moving with a given speed on the moon has a kinetic energy equal to the same, bigger, whatever, if it were moving at the same speed on Earth. So here's the deal. Kinetic energy is 1/2 mv squared, and they're telling us that the weight is different. Well, what we know is that they have the same mass regardless of where they are. Because they have the same mass and the same speed, it's going to have the kinetic energy, the same kinetic energy. Just because the weight changed doesn't mean the mass has changed. Work may be all of the following units except, well, we know work is equal to force times distance. Of course, we know that that's defined as a joule. We have a Newton times a meter. Foot times a pound. Foot times a pound is a force times a distance, and we're left with an erg, which is weird. I've never heard of that before. I have, you haven't. And a watt. We know specifically that a watt is the unit for power, so that has to be the thing that's not a unit for work. The erg is the English, that's our unit for work. We don't use it a lot. Consider 2 engines. The larger is rated at 2 watts and the smaller as at 1 watt. The smaller engine can do a certain quantity of work in 2 hours. The larger can do twice as much work in a time of 2 hours, right? So this is twice the power, which means either twice the work in the same time, or the same work in half the time. And that's where we're at. This is asking about the twice as much work in the same amount of time thing because it's power. 10, we have a concrete block pulled 7 meters across a surface by means of rope. The tension is 40 newtons. The work done is 247. What angle does the rope make with the horizontal? We know when we're doing work that it's only the parallel force that does work on our object, because it's the parallel force during work on our object. We need to do some trigonometry to figure out what's going on. So we want this part of the force. If that's my angle, that's the force times cosine theta times the distance, and that's going to equal the work done. So that tells me that the cosine theta is equal to work over force times distance. So cosine theta is going to be equal to 247 divided by 40 times 7. So 247 divided by 280. In order to find that angle, theta is equal to cosine -1 in your calculator of 247 divided by 280. Oh, sorry, we went down to Brenda. So it's cosine -1 of 247 over 280. That is equal to our angle, and that angle comes out to be 28 degrees when we do it that way. You didn't really have enough room for that. Brenda is carrying a suitcase as she walks along a horizontal walkway to her room. So if we look at the suitcase, we have the force of Brenda and the force of gravity because she's holding it, and then our delta x of 25 meters is in that direction. Because Brenda's force is up and the displacement is over, they are perpendicular to each other. And even though Brenda is exerting effort and burning energy, she's doing 0 joules of mechanical work as we define it here. Number 12, in which one of the following situations will there be an increase in kinetic energy? Kinetic energy is 1/2 mass times speed squared. So what we need is for the speed to increase. As a projectile approaches a maximum height, it slows down. As a box is pulled at a constant speed, it has constant speed. If it's rotating faster, we're getting an increase in speed. That's an increase in kinetic energy. Satellites in circular orbit have fixed speed, so fixed energy, and this is whirled at a constant speed. Anytime the speed is constant, we're getting smaller. Anytime the speed is constant, no change in kinetic energy. Anytime the speed is smaller, shrinking, we get less kinetic energy. 13, an elevator supported by a cable descends the shaft at a constant speed. The only forces are tension and gravity, and so we need to know what's going on. Well, here's the thing. If we look at it, we have the tension that's up, the weight that's down, and we are moving in the upward direction. So that tells me that, isn't we going up? Oh, it descends. I apologize. It's going down. That means weight is doing positive work. Tension is doing negative work because they're in opposite directions, but it's not that they have to be equal. So it's not that tension is larger than weight. The magnitude of the work done by the gravitational force is larger. No, they are the same size because we're moving at a constant speed. The acceleration is 0. Therefore, tension is equal to the weight in this case, which means they do the same amount of work. And since we are moving in the direction of the forces, it's not that they are 0. So we end up with the net work done by the two forces being 0 joules. The tension is doing negative work as the object moves down because that force is in the opposite direction. That force is in the opposite direction of our movement. So it's negative work, but it's the same size as the weight, which is doing positive work. So because of that, the net work done by the two forces is 0 joules. Another way of looking at that is that the net work is equal to the change in kinetic energy. And anytime we have a constant speed, the change in kinetic energy is 0, making the net work 0. 14, we have a woman standing on the edge of the cliff, throwing a stone downward, and outward. And so she's up here. Here's her cliff. She throws one out with the speed v, one down with the speed of v. And we want to know, if she were to throw the stone horizontally outward with the same speed, how much kinetic energy would it have just before it hits the ground? Here's the deal. At the top, we have potential energy plus kinetic energy. At the bottom, when it hits, we have just kinetic energy, and both of those have become the kinetic energy at the bottom. What we know is that even though one stone is thrown down and one stone is thrown out, they have the same kinetic energy in each situation. So they're going to have the same total energy at the bottom. So if it has 450 joules of kinetic energy at the bottom when it's thrown straight down, it will also have 450 joules of kinetic energy at the bottom when it is thrown horizontally outward. Again, there's no direction when we talk about kinetic energy. It's just how much speed we have. There will be other differences, but they will have the same amount of kinetic energy. 15. A rock is thrown from the surface of the earth. Which one of the following statements describes the energy transformation as it rises? If we're including earth in the system, then the total energy is going to remain constant. The kinetic energy is going to decrease and the potential energy increases, so B is out. They do not both increase. Kinetic energy decreases and potential energy increases. That's exactly what happens as it rises. They do not remain the same, but their sum remains the same. Question 16. Complete the following statements. A force that acts on an object is conservative if all forces obey Newton's laws of motion. The object's kinetic energy, that doesn't matter for kinetic energy. Actually, in the definition, it's that the work done on the object is independent of the path of motion. So think about lifting something up or down. That's what's going on. This is our true definition of a conservative force. We've got this pebble rolling off the science hall. We know that it starts off with pure potential energy. All that potential energy is going to turn into kinetic energy. So mgh is equal to 1/2 mv squared. The masses cross out here, so the height is going to be v squared over 2g. So the speed we have at the end is 17 meters per second squared divided by 2 times 10. When we plug in all of those numbers, we end up with a height of 15 meters. That's how high the science hall is. For the next one, we have a roller coaster at the bottom of the hill moving with the speed of 20 meters per second. We want to know its speed after climbing a 15-meter hill. So at this point, we have kinetic energy, and up here, we're going to have potential and kinetic energy. So we're going to take that kinetic energy, we're going to set it equal to potential plus kinetic. So 1/2 mv squared at the bottom is equal to mgh plus 1/2 mv squared at the top, and that's the one that we're trying to find. You can draw the energy diagrams on your own. What we're going to do is find that final speed. So 1/2 mv squared at the bottom minus mgh at the top is equal to 1/2 mv squared at the top. M's can actually all cross out when we do it, so we have 1/2 times 20 squared minus 10 times our height of 15 meters is equal to 1/2 that final speed squared. When we solve for that final speed, it ends up being 10 meters per second, which makes sense. We know that object has to slow down. All right, number 19. Skier leaves the top of the slope with a speed of 5. Her speed at the bottom is 13. We want to know the height of a slope. So they start off with the speed, and at the bottom of the slope they end up with the speed. So if we want to do the energy diagrams with that at the top, we're going to have both potential and kinetic energy. At the bottom, we're going to end up with just kinetic energy, so all of these energies end up kinetic at the end. So potential plus kinetic is equal to kinetic. We're going to build our equations from there. That tells me that mgh at the top of the hill plus 1/2 mv squared at the top of the hill is equal to the kinetic energy 1/2 mv squared. We are looking for the height, so mgh is equal to 1/2 mv at the bottom of the hill squared minus the kinetic energy at the top of the hill. The m's cross out, and so that height is going to be 1/2 the speed at the bottom, 13 squared, minus 1/2 the speed at the top, 5 squared, divided by g of 10, and so that height comes out to be, that height comes out to be 7.2 meters, and again there's a 9.810 difference, and it ends up being 7.3 meters.